atlas. So a smooth atlas is said to be maximal if it's not properly contained in any larger atlas. Sorry. So in other words, this means that there is no other atlas that I will call for now A tilde on X such that A is contained in A tilde. Okay. So another way to say that is that A is maximal if given any chart on X, any chart, let's call them U tilde and phi tilde on X. This chart is compatible with A if and only if this chart is already in A. So in other words, in English, as I put in here, a maximal atlas contains all the charts that are compatible with itself. So all the charts that you need, because you ideally need charts that are compatible with the atlas, with your choice of atlas in order to move around, right? Let's say in order to change coordinates and these things. So maximal atlas gives you that. It gives you all the stuff. Everything else. So you discard everything else is not useful. So everything that's compatible is already in that in the maximal atlas. Okay.
Amir is asking: is a maximal atlas somewhat equivalent to a basis for a vector space?
That's very interesting thing. I guess an analogy will come more clear as we define the notion of smooth structure, because a basis in a vector space specify you stuff like the dimension and these things, intrinsic property it gives you a classification in a way. From that point of view, the smooth structure also gives you the classification of a smooth manifold. So in a sense, there is I guess there is a link somewhat. It will become clear as I in the next slide in some of the comments that I will make. We'll come back to this also.
As a follow-up related to Amir's question, I'd ask: could there be something like a basis for a maximal atlas in the way that there can be a basis for a topology?
That's also another very interesting question. This is probably more suitable to when we are discussing stuff like in another thing on topological vector spaces, this type of stuff. Okay. But it's very, very, very interesting. Okay, so let me just we'll come back to the point that Amir, to this analogy stuff that he was saying. So a maximal atlas on X is called smooth structure. So this could also be defined as the equivalence class that I was mentioning. Some authors do that in some books. So this is where in differential geometry there are some books. You have to be careful what books you pick. There are some authors that use the equivalence class of because the compatibility of smooth atlases defines an equivalence class, and then they use the equivalence classes of that to define, to say the smooth structure. This is why we went through this other route, which is much more cleaner. So a maximal atlas is called a smooth structure. Now, here's the thing. Here's a very natural question. How many maximal atlases are there for X? So I guess this is going back to the Amir's question. You also ask, how many bases are there for a vector for a vector space, right?
Amir has another comment, one word: infinite.
Yeah, okay, that's very interesting thing. I'll say that you will when we talk about In this case, remember, this is a smooth structure. Huh? It's not just any atlas. So this is like a thing. This is an atlas that's maximal, and it's also like it's a smooth atlas, right? Okay. So it's not just any atlas. And this has an implication actually in your answer that is actually, this is something that we will do later when we talk about diffeomorphisms of manifolds, that for certain dimensions, there's I'll comment on that actually in the next slide. So for the time being, this is a very interesting, how many smooth structures are there on X? Smooth structures, huh? We're not saying smooth atlases, smooth structure.
And
so Amir say infinite.
And then there's a comment from Barry where he elaborates on infinite 2 to the 2 to the 2 to the aleph null. But then on second thoughts, which is an interesting second thought, how about 1?
Okay, that's also very interesting. I'll comment on that in a minute, and it will become more interesting in the next session when we talk about classification of smooth manifolds. Okay, so but for the time being, here's a theorem. This is a very important theorem. You don't need to prove this. I actually wanted to provide because I ran out of time and this thing I couldn't do it. But it's on the textbook, and you can find other sources to see this. It's actually not hard to prove, really. It's just a matter of it's a little bit, a little bit time-consuming stuff to do it, which is why I didn't have time. But it's very important. So it says, given given an n-dimensional topological manifold and a smooth atlas on X, there exists a unique maximal atlas A bar that contains A. Okay, so this A bar is called the smooth structure determined by the smooth atlas A. Okay, so the way this is already hinting you, in case you wanted to prove this, the way A bar is normally constructed is the set of all charts in X that are smooth compatible with A. Okay, so if you define this set, you will see that this is an atlas. It's a smooth atlas. This is what the building block for this, a handy thing to prove this. Okay, so a very important take is this, really. So to build a smooth structure on a topological manifold X, you don't need to build a maximal atlas from scratch. In practice, what you do is to use the smooth atlases that you already know how to construct, and then by this theorem you can extend that and have your maximal atlas. In other words, you have your smooth structure on the manifold. This is what people do in practice, and this is also where the confusion often comes, because very often they some people everyone does this. You only denote the smooth atlas as being the smooth structure, but actually without mentioning, they don't mention the thing. Let me go back. They don't mention this the actual maximal atlas that was the atlas determined by A. So when you see some authors, they write only an atlas A and say, this is my smooth structure. In reality, what they mean is actually the other one, the actual maximal atlas generated by that smooth atlas. Yeah. I hope you understand what I'm trying to say here. It's not confusing. So when you see authors, they write, which is a source of confusion, when they only write a smooth atlas, and then you start wondering, but is this maximal or not? Is because they don't mention the stuff. They normally don't omit mentioning this, but it is to be understood behind scenes that they mean the maximal atlas generated by this as for this theorem. Okay, now here's what makes this very important and also very useful, is that this is if you have two smooth atlases, A1 and A2, these are determined by the same structure A, a bar if and only if they are smooth compatible. In other words, if their union is also smooth. Okay, so any two atlases that generate the same maximal atlas means that they are compatible. Okay, which is very handy. So they're already compatible. If they generate the same maximal atlas, it means automatically they are that only happens if they are compatible. So only compatible atlases will generate the same maximal atlas, the same smooth structure. So this is very important.
So the compatibility is an equivalence relationship?
Yes, yes, which is why some people use, as I was mentioning before, the definition of smooth structure as being equivalence class of this, the compatibility of atlases. Okay, so before I comment the thing on the number of smooth structures and these things, which we will do again in the next session, is here's a definition. This is already an obvious definition. So a smooth manifold is just a pair, just like a topological space is a pair of a set of a thing with a topology. In here we have a topological manifold, an n-dimensional topological manifold, and then here we have a chosen smooth structure. We'll come back to this in a minute about how many such a structure. Just like you ask, how many topologies can you generate on a given set and these things. It's also important to ask how many smooth structures. We'll see this is actually a very hard problem. I know we haven't talked about diffeomorphisms yet, but there are some comments that I will go through now in a minute. Okay, so this is it. So a smooth manifold is just a pair. It's just an n-dimensional manifold that together with the smooth structure. Smooth structure as per the definition that we just run through. Okay, so the choice. I was saying this is an analogy I was giving about the topology. In topology, the choice of your topological your topology determines the characteristic of the topological space, right? The underlying topology. So if you change the topology, you might have a completely new, different beast. So similar thing also happens here. If you change the smooth structure, you might have a completely different smooth manifold in a way. Okay, you'll be able to see more of this when we talk about diffeomorphism and this is classification of smooth manifolds. But just to give you, first of all, one thing to note is not all topological manifolds have smooth structures. This is the thing. So you cannot, there are certain topological spaces, and this is actually as a side note here, for dimensions. So it depends on the dimension. So for dimensions equal or less than 3, any topological manifold can be given a smooth structure. This is true. But for dimension greater or equals to 4, there are topological manifolds that you cannot give a smooth structure. And even more, we will see in the next session, even those that you give a smooth structure, the smooth structure is not unique. So therefore, for some dimensions, we'll see actually dimension 4 is one of them. You might have an uncountable number of smooth structures. So smooth structures that are not, let's say, that are not diffeomorphic. So the manifolds are not diffeomorphic. So they are different type of smooth manifolds. So this raises a very good question about classification, especially in 4 dimensions, because then if you are a physicist, you want to model space-time. Space-time is like 4-dimensional, right? I guess So the question is which smooth structure you choose for R4, for example. So it's a very, very, very important question that you will not be, once we talk about diffeomorphism, you will be able to see more of this. But yeah, so the takeaway is that not all manifolds can actually have a smooth structure. Don't ask me now an example, because I can't think these will be like a pathological type of examples, but there are, if you think that I'm happy to share later some example, but you can also search. Yeah, George, you seem like you want to say something.
Yeah, I guess aside from that very interesting question about greater than 4, I'm not sure that even in one dimension you can have a smooth structure. If your chart is a nowhere differentiable function in an analysis sense, or maybe intuitively something like a fractal curve, which is continuous but nowhere has a tangent, I'm not seeing how you could give that a differential structure.
Yeah, I'm pretty sure that there is a theorem that shows this, that in principle you can construct, you can give a smooth structure for any topological manifold for dimension less or equals to 3. But I will double check you on that, because these are like very like important results and these things. And very often the constructions are a little bit tend to. But yeah, I'll double check on that. So you are saying you are not sure for dimension 1 whether actually anything. Have you seen examples of a manifold? Well, I will find a theorem, actually, a specific theorem that results that show that that says that for dimension less or equal than 3, it is feasible to equip a topological manifold with there is at least a smooth structure. Whether it's interesting or not, that's something else. But there will be at least the thing, as always. There's at least one. Whether it's useful or interesting is another thing. But I'm pretty sure
Okay,
there's construction.
That might be the catch. Okay, that might be the catch, that it's not useful.
It might not be interesting.
Yeah.
It might not be useful or interesting, but there is the thing, as always in maths, often these catches.
Because I just remember from real analysis, it was kind of shocking that you could have a function that not merely has jumps in the derivative, but that has jumps everywhere, that it's all jumps.
Yeah. Yeah. But in the next session, you will see more what I mean, especially for dimension 4, for instance, that you will see actually there are an uncountable number of smooth structures. An uncountable, huh? So not even countable, an uncountable. So
oh boy.
It doesn't tell you the thing. It's also a deep result that has been proven. Obviously, we won't try to prove it, but just to emphasize. And in some dimensions, they actually specify, okay, there are like 3 or 4 or 5. They give you a precise number of the thing. We'll get to that, but just to let you know, this is very very interesting, especially if you are doing the guys in physics. You want to model space-time. The question is, in 4 dimension, which smooth structure do you choose to model your space-time with, and these things. So yeah. So the choice, we will see the choice of the structure will matter a lot, of your smooth structure matter a lot in some dimensions. So we'll come back to that in the next session, when we talk about classification of smooth manifolds, when we cover diffeomorphisms from manifold to manifolds. The second part of diffeomorphism, we had the first part, which is diffeomorphism only defined on the thing from Rn to Rn. We'll have more abstract on the thing from two manifolds, or from a manifold to itself. The thing. Okay, so I have impression. Amir, did I say I would go back to your? Okay, so let's say Barry. So I hope this is already hinting you that your thing about one smooth structure and these things, that actually there's more into it It depends a lot on which dimension you are talking about. Yeah. Session you will see actually. And you will actually see that there is actually there is some way where there's actually one smooth structure. So you might be right on that, but we'll come to that on the thing in the next session when we talk about the classification of smooth manifolds.
Yeah. Okay. Yeah. But we lost Bamborde for a minute there. It's a connectivity problem. But your last question, Barry, I would say in the jargon, has already been answered. They say that on Zoom a lot. The question has been answered live.
Okay. I am back. It seems the thing threw me out. Sorry for that.
And I was just saying to Barry that I think his last question has already been answered just before we lost you, which is that we will cover this in a later session.
Yes, which question was that about the number of smooth structure where he hinted
Yes.
one?
Yes.
Yeah. Okay. Yeah. In the next session, when we talk about classification, you will actually see. But in general, there are manifolds with many smooth structures, including an uncountable structure, as I was already hinting in dimension 4, for instance. But we'll get to that once we talk about classification, diffeomorphisms, and these things in the next session. So, yeah, go ahead.
Barry has to sign off, but he will be able to catch up on the replay.
Yeah, sure. I will also re-edit this because obviously there was like some interruption, and also when I miss out the other slide, so I'll make it easy for you. That means I will probably upload this on Monday because of the editing thing.
Yeah.
So sorry for that. Okay, so here's the challenge. So this challenge is really like well, it's not simple because you still have to do a lot of work. So it's to prove. So the good thing is you already know that these are smooth manifolds. So all you have to do is to actually prove it by constructing smooth structures on them. Okay, so for Rn, for instance, well, the hint is look at the stuff of maximal atlases and this type of stuff, how you detect, and and I always forget to include your thing. There was a test book that you shared, George.
That would be the Spivak, which I like actually because it's not a textbook. It's a very short, what they used to call a monograph, a long essay rather than a textbook.
Yeah. So that will be the thing for those of you to revise the notions of these differentiability stuff, all this stuff that you need. Because essentially now go ahead.
I can put that in the chat, and it's also being put on the Discord, but never hurts to repeat.
Yeah, I went there when I was rushing to do the slides, but because the thread, there have been so many new threads, I couldn't quickly see the link. So so I definitely recommend, because obviously, as you can see now, this is all like calculus stuff. It's just about playing this thing. Outsourcing. Computation from the manifold to Rn.
I think
we'll use that.
I think it will be very important for people to actually review the multivariate calculus, because I hate to say this, a lot of the courses are not good. They quickly just add a semester on to single variable calculus. So
Yeah.
I think it would be good for anybody not sure to review those multivariate calculus.
Yeah, it is very important, especially if you you want to work with higher dimensional manifolds, right? So you need to feel comfortable with this.
Okay, I found the link.
Okay, thank you. This is another book, and then obviously these guys. I don't know if you've been following. Obviously, their style is slightly different than my style. How do you find these books? Which one do you prefer?
Well, I'm liking Lee in that he's very methodical and thorough, but it's
Okay.
2 books. I just started looking at the Loring 2 book, and that one I'm loving a lot, but I'm not sure if that one would be for everybody. But I myself am
Okay.
now liking that one the best.
Okay. Yeah, I mean, this is the thing. There are. It's a matter of sometimes you have to. There are some parts where one of them is better than the other, and these things
Yeah.
is just a way of moving it. Yeah.
But
There was another one that. Yeah, go ahead.
I think it is good when you're really trying to learn something fast, a crash course, to refer to multiple sources that cover it from different angles.
Yeah, correct. This is the thing. One of the challenges of really learning this type of topics is that the stuff, the notions can be defined in so many different ways, and from so many different angles that um, it can be confusing if you are taking
And we're also not doing the
on the
other.
other hand, if you land in the wrong one, you feel you lose the motivation to keep on.
Yeah, I find this a lot. That's one author's approach might not work for me, although it works for other people, and the approach that works for me might not work for somebody else. I think it depends on your individual mathematical mindset, say whether you're more algebraic or more geometrical.
Yeah. Okay. So, was there anything?
I see something. Oh
Oh,
no,
the
that was
poll.
just me. I put the that was me. I put the Spivak reference in the chat. That's all.
Yeah, I forgot the poll, but I guess
Is there
at this stage
anybody
people will
left?
probably want. Yeah, not many left, so it's uh, November the 12th or November the 19th, I think. Let's see.
I'm a bit torn. The part of me wants to jump ahead as quickly as possible, and the other
Yeah.
part of me is concerned with people being left behind.
Yes. That's the thing. I mean, I took this approach of small doses
Yeah.
each time and these things just to make it easy for people to digest and the thing. But yeah, it might still be very very hard if you don't take a little bit of time at home and these things to go through these things. Okay, now the poll is not visible. Now it's visible. Sorry for that.
Okay, yes, I see it now. It's November
I hope I
12th.
got the dates okay.
Yeah, that 2 weeks or 3 weeks.
Yeah.
I'm going to put my
I mean,
vote
not
in.
much. Probably 2 weeks. That's what I think. So while people are voting, I will just go back again to say. So yeah, so this is it. So you now know what a smooth manifold is, and all I would say that the actual main thing of a crash course is actually done. Obviously, we want to talk about diffeomorphisms and these things, but still, at least you know the definition of a smooth manifold. Okay, so you are in a good in a good shape to understand what a Lie group is, because as the say is a different. Actually, in here, there's technically we have to say it's a smooth manifold as opposed to the thing. Obviously, a smooth manifold is a differentiable manifold because it's also a CK. You can differentiate it many times, C1, C2, and infinitely many times. So, from that point of view, for those of you after next session, for those of you who don't want to maybe jump into other extra stuff that we plan to maybe continue with, like fiber bundles and this type of stuff, you can jump off ship. You don't have to. Attend the extra stuff. You can maybe take an opportunity to revise again in order to understand these things.
I have one question, but this might relate more to extra topics. Are we going to cover differential forms, or would that relate more to fiber bundles?
It depends on how deep we go into it. They are definitely worth mentioning because they are very, 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 very useful. So we might do that. Let's see how we go and how many sessions we take. Ideally, I want at least 2 or 3 people. It makes it easy to think.
Fair enough. Yeah, I mean, for myself, I'm trying the books go into that a bit, and Spivak goes into differential forms a bit too. So for now, I'll just consider that extra reading.
Yeah. I mean, even in the next thing, in the next session, I think we should probably have some extra time after we discuss diffeomorphism and this, and even in the next session to talk about to talk about the class, the thing, maybe Poisson algebra, something like that. The class of smooth the vector space of smooth maps on a manifold and these things, and also talk about the tangent space, this type of stuff.
Yes, it kind of comes down to the abstraction pill that if you've just taken multivariate calculus, you're used to playing around with a lot of coordinates and stuff, and the differential form is like the abstraction of that.
Yeah, that's it. The thing of the thing. For those of you who feel comfortable with the calculus and this type of things, a lot of the stuff that you're already doing, all these abstraction is just a formalization of that. Putting it in a much more in a rigorous footing. So you won't struggle. You will be able to associate the abstraction with the stuff like you were already doing without knowing.
Yeah. I like that.
So
The Socratic method. You already know it. You just don't know that you know it.
you just know it. Yeah, you were already doing it. Like chart transition stuff. People were already doing it. When you you do the exercise is asking you one thing to move from Cartesian coordinate to polar and these type of stuff. You were already doing chart transition without knowing.
Yeah.
Okay. Good. So I guess there is nothing else in the text. So we make it on the final session of the normal. Where is it? So the final session of manifolds 101. And then the idea then is to have a few extras where we cover the more advanced stuff for those who for those who like George, who are keen into going into the other stuff.
And I repeat my offer to do a study session next week on the Oh my God, my arithmetic's gone. Whatever a week from today, is that the 6th or the 5th? The 5th.
Yeah, the 5th, I think.
Yeah, next Friday I will again have a study session. And again, I encourage people for whom that isn't a good time to find someone else in their time zone to have a study session with.
Yeah, I encourage also. It's absolutely it's necessary, especially now. Now that we are getting into the nit and grit of the objective, really, of what's needed, because this will help you. If you don't have this the stuff, you will struggle on the Lie groups when we start dealing with the Lie groups and these things. So it's a great opportunity for you. Okay. Good. So I guess there is nothing else. So yeah, thank you again, George, for your help. Yeah, I see you are posting thing on the chat. Yeah.
And thank you, Bamborde. It's really reawakened my interests that have been dormant for a while.
No, thank you. It's always a pleasure. I mean, this crash course was all about because I realized that jumping straight into big groups and these things would probably be like thing a bit of it will be essentially harder for me to think than doing the crash course for people to know what a smooth manifold is, and then it's much more easier to take the people on the journey.
It's almost a joke that any more advanced book you read, in the preface or the introduction, they'll say, "Oh, all you need is calculus and linear algebra."
Yeah, no, yeah, there's a lot. I see that a lot in quantum computing. The thing. In fact, I was recently in one of these meetups where I was shamelessly promoting the initiative, the courses, saying that the quantum gates, they don't just they're not just matrices that you multiply, and these things. They have actually a very rich structure, right?
Yeah.
The group structure, they have the geometric topological structure of a smooth manifold, these type of things, that if you want to go to the next level, you need to be aware of these things, because they are like tools for you in order to do useful stuff. So yeah.
Yeah, I guess the converse would be that if the gates didn't have a nice structure, you couldn't define, you couldn't say what you can and cannot compute with them.
Yeah, it's true. Yeah, that's also very interesting observation you did. Yeah. And also this thing, things like manifolds and these things, they're not just useful. Obviously, the overlap with other things. If you are interested in topological data analysis, for instance, manifolds,
Yeah.
Very useful to know what they are. And in our case, this actually saves us when we do. There is a course that we will definitely do on algebraic topology. So we already have the notion of manifolds already out of way. The notion of all this topological stuff also out of way. So it's like also serves as a prerequisite for that. And you are right also about the non-commutative geometry thing. So yeah, so you definitely need several basis before taking the course. One of them, obviously, functional analysis and the measure theory, and this, but algebraic topology also will help. And yeah, so all the pieces here will be the stuff that we will go from now on will be very useful for those of you on this thing, long journey. Who knows where it ends? It will not end. There will always be a course. I'm trying to get my other colleagues to come and provide, so that way we go a little bit faster at these things. There might be one my colleagues might do a course on algebraic geometry, especially for guys interested in cryptography and this type of stuff. So that might also be useful. Yeah, but anyway, step by step, we started very simple from the foundation module with the finite dimensional vector spaces, this type of thing, and these things, and now we are here, and hopefully we go to Lie groups. We then go to cover a decent amount of measure theory and functional analysis before then we go even higher. And hopefully these things will be useful, especially for those of you who are interested in applied stuff, right? So the physicists definitely, the guys in physics, these in particular this crash course stuff, these notions. If you want to understand general relativity and these things, you need to to master smooth manifolds. I mean, depends on how we adventure. We might even adventure into more specific type of manifolds as we go along. Let's see how much extra we can do. Maybe touch a bit of a Riemannian geometry, a bit of that. Now that, so maybe, if you are curious about general relativity, maybe we can, yeah.
Yeah. For myself, I'm interested in low-dimensional geometric topology. There seem to be some things which are special in low dimensions, where if you just talk n dimensions for n high enough, don't even occur anymore.
Yeah, that's the very interesting thing of. Incidentally, if you are looking for like an applied person, you're looking. It's a bit annoying, but from a mathematician point of view, it's very interesting that certain things occurs in a thing. In some dimension and others don't, and these things and all these pathological stuff that you have, and very hard problems, open problems, like the classification stuff that we will touch on in the next session.
Yeah, I mean, yeah, very difficult, like millennial problem difficult.
Yeah. We might actually comment on the thing. Maybe in the next session, I will see if we have the thing to comment on the Poincaré conjecture that the guy, he won 1 million, but he didn't claim it was solved by Gregory Perelman.
Yeah.
Yeah, actually, I think next session is actually a good opportunity to mention that to the thing. What the thing is, because we already have all the languages that we need about the thing in order to not understand the proof, because the proof is very complex, but at least understand the problem, the problem that the thing was the open problem, and then the thing, the implications of it and these things. Yeah. Okay, good. So I don't want to take much of your time, George. Thank you so much again. It's been very interesting. And I look forward to seeing you in the next session. Thank you. Thank you, everybody, also for staying this late.
Thank you. And I would also like to thank Amir and Barry for very interesting questions. I know Barry had left, but maybe if Amir's still here, thank you.
Yes, Amir's still here, and Claudia, thank you for staying all this the follow-up. Yeah, you are the brave ones, because the thing, as always, these things, the drop-off rate is as the thing gets more complicated, and these things, people drop off. But don't give up. This is all like it might, like, especially for the first time you are being exposed to this. Remember, just take your time. Go through, revise stuff, and take the opportunity if you can join George or another person to just go through stuff, check different references and these things. That's what you have to do, and then things will come to your mind.
And just recheck the definitions very carefully. Anybody that followed me last weekend saw me trip over my feet by not doing that and making a mistake. But I am not afraid to put that out there, because I have nothing to lose. But I think it's important for any students of any subject not to be afraid to make a mistake, because when you make a mistake and review where you went off the tracks, that's when you really, really learn.
Yeah, absolutely. Absolutely. And you probably find, if you find actually the thing, mistakes or something on the definitions along the way of all these series and these things, you can correct me and these things.
Yeah.
it's not it's a thing. It's actually part of the learning and these things. Probably there might probably be a lot of this stuff there. Because I learned these things like many years ago, and these things, even me, for me, it's like coming back to these things like again after several years is a little bit. So yeah, that's a good point you make. You made. Don't be afraid of making mistakes. It's natural. I mean, these things are not very very easy stuff, right? So it happens. Especially when you have layers of abstractions and concepts, trying to piece them together. It's not the thing. It's not easy at all. Okay, good. So George, thank you again, and we catch up in next week. So I will upload the video probably on Monday because of the editing and these things that I have to do.
And I guess the slides will be available on Monday too, I guess.
No. I'll put the slides there now.
Okay, good.
The slides will be available as soon, so people can get. Yeah, so that's a good point you made. So the slides definitely will be there. I'll put them in the next few minutes. I don't think I left any slides. Anything that I forgot to add. If I did, I'll double check again. Okay, good. So thank you, and have a good weekend again.
Okay, yeah. Bye. See you in 2 weeks.
Thank you. See you in 2 weeks.